Hi, my name is Mark Schvetz. You already know this by now, and I'm a developer at Chariot Solutions. Every year, I'm amazed at how we're able to get these awesome speakers. And Richard Feldman is living the dream of programming in a purely functional language, no red ink, not only on the front end, but on the back end as well. He's an amazing speaker, and we're so lucky to have him close out our first day. This great talk is about our past, and of course, the thing we care most about is the future. Thank you all for being here and making this conference possible. You guys are all professional at Zoom attendees now, so just use the Room A Slack channel. We'll try to answer all the questions that we can towards the end. Richard.
All right, everybody see my screen okay?
Yes.
Great. All right, let's dive in. This is the next paradigm shift in programming. I'm Richard Feldman. So a week ago, I saw this headline, New Jersey needs COBOL programmers. And this is a bit of a surprise to me because COBOL is a pretty old programming language. For those of you who are not familiar, COBOL was originally developed in 1959. So for a little bit of context, that was when Dwight Eisenhower was the president of the United States. And Alaska and Hawaii had just become states that year. So definitely an old school language. At the time, and in fact for many decades, COBOL was the #1 most popular programming language there was. Now obviously that's no longer true today. Today it's a relatively obscure language, but there's still a ton of COBOL being written and in fact existing in the world, powering a lot of business transactions as legacy code. So essentially what happened is, as is the way of things, over the decades, COBOL peaked in popularity and then eventually declined in popularity. And this is sort of the normal way of things with software. We're technologists. We develop new technologies, and that means that other technologies inevitably peak and then eventually decline in popularity. And then the technology shifts to something else. This has happened with COBOL. It's going to happen again with other technologies. So this is COBOL in 1959. Believe it or not, COBOL itself was actually part of one of these paradigm shifts in programming. So the procedural programming paradigm was something that didn't exist until the late 1950s. COBOL was part of the first batch of that, along with ALGOL, which is another very influential programming language, and Fortran, another very influential programming language. These were all part of the shift towards the procedural programming paradigm. This is a paradigm shift. Before that, we had assembly language and other even older languages, which did not have procedures. Procedures, AKA functions, AKA subroutines. Back in the day, all there was jumps. You would just jump around from one line of code to the next, and there was no first-class concept of procedures until these languages sort of introduced them to the world. So a programming paradigm is about both features as well as style. As you can imagine, once you have procedures as a tool, your code starts to look different. You start to write in a different style, organized around the concepts of procedures and functions that are sort of driven by that feature. So the feature of procedures change the style of programs, paradigm being about both. So zooming out a little bit, this is late 50s, this paradigm was introduced. As we know, this is still a paradigm that is in wide use today, procedural paradigm. In fact, it's so ubiquitous that we pretty much take it for granted at this point. That's just what programming means, is you have procedures, you have functions. And I think it's safe to assume this will continue well past 2020. I don't really see any paradigm shifts in our near future away from the procedural paradigm. But worth noting that paradigms being about features and style, they can overlap. It's not like you just have one paradigm and that's it. That's your one and only paradigm. There are many different paradigms in software and they often overlap. And so when you see a paradigm shift like this, sometimes it's towards something that lasts like this, and sometimes it's away from other things. And over the course of this talk, we're going to see examples of both. So the question of this talk is, what will be the next paradigm shift? Like, what's the next big thing that is a shift that has not yet happened, but which I think is going to happen? And that's the point of this talk. What is that shift going to be? So we're going to look at 3 different paradigm shifts. So the first one, that was a very important shift, is the structured programming shift. Next, we're going to talk about the object-oriented shift, which is something we're probably all familiar with. And then finally, we're going to talk about what I think will be the next paradigm shift. Okay, let's start with structured programming. So for those who are not familiar with structured programming, it's essentially the idea of blocks. So here's a conditional in Python. You have if followed by the condition, and then a block of code, and then else, and another block of code. And we're all pretty much familiar with structured programming in the sense that this just looks like normal code to us. Yeah, you run if, then you have some code, and then you have else, then you have some more code. And we know that when the program comes in, it's going to run either the first block of code or the second block of code, and then it's going to run whatever code comes after this conditional. But that wasn't always the way that it used to be. So here's Fortran. This is a language, remember, that was one of the procedural programming languages. Fortran did not yet have structured programming. So this is a Fortran conditional. If, and then we have the condition being boats minus 1. So that is, take the number of boats and subtract 1 from it. And then rather than if, then else, we just have if boats minus 1, and then these 3 numbers, 3, 7, and 12. So these 3 numbers correspond to lines in the program that it's going to jump to depending on the value of that condition. So to use pseudocode, this is not Fortran anymore, but if boats minus 1 is less than 0, go to line 3. If it's equal to 0, go to line 7. And if it's greater than 0, go to line 12. This is just how conditionals worked in Fortran. You would be jumping all over the place in your program. And as you can imagine, let's say you took the first branch of the conditional, you go to line 3, you keep running, and then you hit line 7. Well, if you haven't jumped before then to something else, all of a sudden now you're running the second block of that conditional. So this was what led to program structures that looked kind of like this, where you'd have this control flow that was just jumping all over the place, forward and backwards along the program, looping back on itself. And this diagram, which kind of looks like noodles, came to be known as spaghetti code. This is the original use of the term spaghetti code. It specifically referred to jumping around forwards and backwards in your code with conditional jumps, as opposed to structured programming where you used blocks instead. And in 1966, there was this thing that came out called the structured program theory, which proved, actually, if you have blocks for things like if and also for loops and procedures, you can express any program that you can express with jumps, which means there's essentially no downside to doing things in that way, and then you can get rid of all the spaghetti code. So essentially, the structured programming paradigm shift was going from the thing on the left, which is to say the Fortran version where you're doing conditional jumps, to the thing on the right where you have conditional blocks instead. So the structured programming idea of using blocks instead of gotos to express conditionals, loops, and procedures was a big paradigm shift. So this is the second one that we have on our timeline here, structured programming. This first appeared with Algol. So not with COBOL. Algol was like around the same era as COBOL, but COBOL did not have this, Algol did. And remember, a paradigm is about not just features like blocks, but also style. And as you can imagine, if you have that feature, you can program in a structured style quite well if you have the feature of blocks. COBOL did not have language level support for blocks, but some COBOL programmers still embrace the style anyway. So here's an example of a post. This was from actually 1979, which is almost 2 decades after structured programming had come out. And it's about how to do structured programming in COBOL. And essentially, this is a piece that's saying, here's how to write in a structured programming style as if we had blocks, but writing it using these jumps since that's really all we've got to work with. So quote from the piece, the motivation for applying structured programming techniques is to produce programs which are easy to read and maintain. Sound familiar? It's possible to design programs using these techniques and then translate the design into COBOL. So the idea was, although COBOL doesn't have those features, we can still sort of emulate them using the features it does have. And this is also going to be a recurring theme throughout the talk. This is a thing that we do with paradigms. If we don't have first-class language level support for it, oftentimes we will emulate it anyway because we think the design is good. All sorts of books came out about this at the time. So you have COBOL with structured programming, structured COBOL programming, on and on and on. The idea of writing COBOL in a structured way, even though COBOL did not have first class for structured programming, was quite popular for a long time. Dijkstra had a real barn burner of a quote here. The go-to statement should be abolished from all higher level programming languages. It is too much an invitation to make a mess of one's program. This was 1968, so about a decade after structured programming came out. The title of this post was Go-to Statement Considered Harmful. So if you're ever wondering where that sort of title style came from, go-to considered harmful was the original one. Now we have blank considered harmful. They're all derived from this one post. And essentially what Dijkstra's saying here is, look, we have structured programming. It's been a decade. We've seen that it's good. We have the structured program theorem showing that we're not missing out on anything. You can express any program we could with all these jumps with structured programming. Let's get rid of the foot gun. We don't need it anymore. We can move past it. Now, a reasonable question here is, okay, yeah, but why not have both? Like, why do we need to get rid of the other thing? Why don't we just have go-to and structured conditionals? What's the problem? Well, it's a reasonable question. And in fact, C does have both. Here's some C code, in fact, that's using both in the same thing. We have a structured programming style conditional with blocks, if then else, and then in the middle of them, they're calling go-tos. So yeah, you absolutely can have both. But that's not really where most of the industry went. Generally speaking, people went with Dijkstra's advice, and subsequent programming languages tended not to support this style at all. Go-to is much, much, much more rare today than it was in the 1960s when it was ubiquitous. So this is an example of a paradigm shift that went away from one style and towards another style. So procedural, we just got it, and everybody uses procedures now. Structured programming, not only did we get and use blocks, but by and large, not everybody. I mean, C still to this day has Goto in it. But by and large, everybody shifted away from the old way of doing things. Okay. So speaking of things that people have shifted towards, there's this company called /Data, and one of the things that they do is they do research on like how programming languages are used. And last year they came out with this global developer population report for 2019, talking about sort of the most popular programming languages out there. So here's the list. If you haven't seen this list before, it's probably going to come as no surprise. JavaScript, Python, Java, top 3 most popular languages, followed by a bunch of other languages whose names you probably recognize. There's C in the middle there, the language that still has go-tos, in addition to structured programming. But you might notice that there's another paradigm on here that is quite strongly represented. To be blunt about it, there's C, and then there's OOP. Every single other language on here is object-oriented, among the most popular languages. So this is not quite the level of dominance that we saw with structured programming and procedural programming, since literally all of these languages, 10 out of 10, have both structured and procedural, but OOP comes close. It's a very, very dominant paradigm right now in software. So let's talk about that. Let's talk about the shift to object-oriented programming, which clearly has happened. Well, first thing to note about this shift is that, again, it's a technique. You can do it. We saw books on object-oriented COBOL. COBOL was not an object-oriented language. We saw object-oriented Fortran, even books on object-oriented C. I mean, C literally is not an object-oriented language because C++, its successor, was object-oriented. But yeah, if you wanted to, you could still write these in an object-oriented style. We'll talk about what the object-oriented style is a little bit later. But it's worth emphasizing just how dominant this paradigm became in especially like the mid-90s and early 2000s. There's this great quote, Joe Armstrong, the co-designer of the Erlang programming language. He says, criticizing OOP was rather like swearing in church. O-ness became something that every respectable language just had to have. And he mentions this in the context that people would ask him if Erlang was object-oriented. He didn't really feel that it was, but he felt compelled to say, oh yes, of course it's object-oriented, because he didn't want to be on the wrong side of that and be accused of being some archaic pre-OO language. If you want to read the rest of his quote there, there's a link on the page there. So looking at these top 10 languages, it's worth noting that objects first appeared before object orientation did. So objects first appeared in the Simula programming language in 1962, and at the time, it was just used for simulation. So the classic example that they would give in Simula is a hospital simulation. So each staff member is represented by an object, patients are represented by objects, they all have their own state, they're all interacting in various sort of autonomous ways because it's a simulation. That's sort of the whole point, is that they have these autonomous actors, and they wanted to be able to add new ones on the fly with their own autonomous logic. The idea of objects for simulation was what Simula did, but the idea of expanding that to be objects for general purpose programming, just like all sorts of different contexts, like these top 10 most popular languages, which are not simulation languages, that was object orientation. So Simula was the first language to introduce objects, and we can see it sort of appear as one of our paradigms here, along with structured and procedural programming. But object-oriented programming came actually significantly after objects first appeared. The coin was termed in the late 60s, but the first language to introduce object-oriented programming to the world was Smalltalk. So Smalltalk was created by Alan Kay. He coined the term object-oriented programming in 1967, and then led the team that developed Smalltalk in the early 70s. He collaborated with this guy, this is Dan Ingalls, and Dan was the implementer of Smalltalk. He worked with a team of people to build out the language. Also, a fun piece of trivia about Dan, among his other contributions, he also invented menus, like, pop-up menus. There's a lot of influential stuff going on around this project. There's this amazing interview from 1989. So this was actually after object-oriented programming had been a thing, but was not quite yet dominant the way that it is today and became in the 90s. It's Dan Ingalls talking about object-oriented programming. And what's fascinating about this interview is that because this was before OO became dominant and something that we could take for granted, this is presented as sort of a pitch for OO. He's saying like, hey, here's why you might be interested in this new thing called object-oriented programming. And I want to just play you a 60-second clip of Dan talking about this in his own words.
Please join us in welcoming Dan Ingalls.
I had the good fortune to participate in the Smalltalk project with Alan Kay and the other good people who worked on it. And it was an interesting project. We designed a programming language and then used it to build an operating system and a graphical user interface. and then built on top of that a whole programming environment consisting of editors, debuggers, compilers, and then used those to implement several large applications, such as a music system and an animation system. And then we had the opportunity to do something which most other projects don't get to do, which is when it was all built, instead of going commercial and delivering it, we got to throw it all away and do it over again the way we would have wanted to do it. And in the process, we got to find out about complexity because the applications were quite complex. And we had a chance to try out several solutions to dealing with that complexity.
So one of the things that I really appreciate about the way Dan talks about this and sort of tells this story of what they were doing with Smalltalk and building this operating system and these graphical user interfaces on top of it, and then sort of rewriting the whole thing and doing things the way they learned, is that he talks about it in terms of this is something that was an experiment. It was something that we tried. We didn't necessarily know what the results were going to be. We had an intuition that this was going to be a good idea. And then what we did was we tried it out and iterated on it, rewrote the whole thing, and then did it sort of the way we wanted. And then here are our results. So this interview was in 1989. And one of the things that's sort of striking to me about this interview is that this would still work as a talk today. Like imagine a talk today where sort of the headline of the talk is blank is a solution to complexity. I think the reason that talk would still work in 2020 for whatever blank you want to fill in there is that in 2020, we still have a big problem with complexity. Like later on in the talk, Dan goes on to talk about incidental complexity versus essential complexity. Sound familiar? So this is clearly something that to the extent that object-oriented programming may or may not have helped with this, it certainly didn't solve it. So the idea that object-oriented programming is a solution to complexity, I don't know if that is sort of borne out by the experiment. I think it's worth asking 31 years after this interview was conducted and more than 40 years after the term object-oriented was coined, is like, hey, how did this experiment actually go? Did it actually give the benefits that we expected? Or is there a reason that there's still all this complexity and maybe it didn't help as much as we thought it would, even though it's now dominant and everyone's using it? So one of the other things that Dan talks about in this talk is modularity. He says, the principle of modularity is if any part of the system depends on the internals, and that's a very important point to emphasize, of another part of the system, then complexity increases as the square of the size of the system. So basically, if all you have is a way of having sort of like public interdependencies and every part of your system can depend on every implementation detail of every other part, you get this sort of combinatoric explosion of dependencies where if you change the implementation details of one part, it could potentially affect any other part of the system. And the bigger your system gets, the bigger and bigger of a problem this gets. This is absolutely true. This is a big sort of known driver of complexity is too many interdependencies. And modularity is a way of fixing that. But it's worth noting that modularity is not an object-oriented concept. It's decoupled from object-oriented programming. In fact, there's a whole paradigm called modular programming. It's where you sort of are able to define a public interface to hide private implementation details. There's a language called Modula, which actually introduced the first class concept called modules, which is a thing we're all familiar with today, which lets you do this, define a public interface to hide private implementation details. Before there were modules, there was a different thing called encapsulation, which lets you define a public interface to hide private implementation details, but just about an object's state. It's less general than modules. It's only for objects. And this is what Simula had. And the reason that Simula had encapsulation but not modules is pretty straightforward, which is just that Modula didn't exist yet. Simula and both Simula and Smalltalk predate Modula by several years. So objects appear with Simula in 62, object orientation appears with Smalltalk in 72, and modules first appear with Modula several years later. So this is the beginning of modular programming, which once again is a paradigm that has persisted to the present. In fact, if you look at these top 10 most popular languages, the languages with module systems today is all of them. Some more recently than others, but eventually over time, every language seems to have concluded, you know what? Modules are a good idea. We should have them in our language. And that includes all of the languages that had encapsulation before, which is to say, all of them except for C. So encapsulation in practice proved to be not quite enough, and what people ended up wanting is modularity and modules in the form of modules in addition to that. Worth noting that modular programming as a paradigm was also something that people were willing to do as a tactic, as a style, as well as something that they were going to be doing with language features. So here's an article from 2001, Modular Programming in C. This is well before C had any inkling of having a module system. But of course, you could write as if you had modules and try to follow conventions and use the language features C has to try and enforce these public and private separation using discipline and programming technique rather than using the language feature of first-class modules. This gentleman right here, Bjarne Strauss Trip, is the creator of C++. And he is responsible for 6 out of 10 of the most popular languages today, because 6 out of 10 of the most popular languages today are either a descendant of C++ or C++ itself. So Smalltalk was a very influential language. C++, wow, incredibly, incredibly influential language. But it's worth noting that Strauss Trip with C++ and Alan Kay with Smalltalk were coming from very different perspectives on object-oriented programming. To be very specific about it, Alan Kay had a quote about C++, which is, "I made up the term object-oriented, and I can tell you I did not have C++ in mind." He saw C++ as having gone in a very different direction from Smalltalk. And really, C++ was, although it came chronologically later than Smalltalk, it was not a descendant of Smalltalk, but rather they both had a common ancestor in Simula. So Alan Kay looked at Simula and said, I had these objects are really interesting. I want to try and apply this to an idea of applying design systems based around objects to everything else, to a more broader purpose than just simulations. And Strauss Trip was working on a project where he wanted to use C, but he wanted some more robustness. He'd had a good experience in the past, in previous work, doing simulation work, and decided that, you know what, I want to take some of these ideas from Simula and bring them to C so that I can make my C more robust in various ways. So here's our timeline again. We have assembly language, Simula, and C. C with classes was actually the predecessor to C++ that Strauss Trip developed first. We'll talk a little bit more about C with classes in a second. But C++ was of course the one that really took off, that was really influential. C with classes turned out to be just something of a stepping stone, but a very important stepping stone that revealed something important about object orientation along the way. Modular programming, by the way, worth noting, came before both C with classes and C++. So this was something that was already out there, already known with Modula, but Strauss Trip didn't choose, or perhaps wasn't even aware that this was a thing back when he made C with classes and then C++. And it wasn't until much, much later that those languages developed module systems, even though the technology was available at the time. One of the important lessons here is that just because something's a good idea, like modular programming, in fact, modular programming has now become a completely dominant paradigm where every modern popular language has developed a module system. At the time, it was still something where it's like, maybe we don't need it. Maybe it's not a thing. Now, in hindsight, we can look back and say, well, clearly you should have added modules back then. That would have saved you a lot of trouble over the years. But hindsight is 20/20, as they say. We didn't necessarily know that, or he didn't necessarily know that that was going to be the case many years later. Of course, now that they do have modules. So Strauss Trip also gave an interview, much like Dan Ingalls did before, and we're going to watch a little clip of that, in which he talks about the sort of the evolution of C++. And one of the questions that he answered was about regarding C with classes, like why did he pick C to build on, and also why did he choose to add classes to C? Why not just use C as is? So as to the question of why pick C, he talks about, well, look, it's the best systems programming language available. It's flexible, it's very efficient, in terms of performance. It's portable, I can compile it to many different targets. It's available, like everyone can use it for free, and it's known. It's familiar to a lot of programmers. I thought that was kind of interesting that even back in this era, in the 70s, it was still the case that familiarity and sort of the avoidance of reinventing the wheel was as strong a cultural thing then as it is now. Maybe not as strong, but it was still at least a significant factor for what Strauss Trip's considerations were for why to build C. So here's Strauss Trip.
This area, if you want to build a new language, a new system, it's quite useful not to have to reinvent every wheel. So I took the attitude that computation as such was a problem solved by Dennis Ritchie in the design of C, and my business was program organization. Clearly, C is not the most beautiful language ever. There's a lot of flaws, but they're second-order flaws. I consider the C declarative syntax an experiment that failed, but it's not critical. I never met.
So this part I actually thought was kind of funny. I just want to reiterate, this is Bjarne Strauss Trip, the creator of C++, in 1994, saying C syntax was something he considered to be an experiment that failed. This, by the way, is C syntax, like curly braces, function calls with parentheses, semicolons at the end of the line. That's the syntax that he considered to be a failure, a failed experiment. Which is kind of funny, with hindsight, because now it's like, oh, well, how did that turn out? C-style syntax, it's all over the place. 7 out of 10 of the top 10 languages use C-style syntax. The only ones that don't are Python, Ruby, and Objective-C. Everybody else is all curly braces, parentheses for function calls. The most controversial choice they make is whether or not they have semicolons. But C-style syntax absolutely took over the world of programming. And today, going back to that case for familiarity, in fact, a lot of times, if you see a new language comes out and it does not have C-style syntax, that's considered a downside. People say, oh, this is very unfamiliar. This is going to be really hard to learn because it's not like our familiar C-style syntax that everybody knows. But from Strauss Trip's perspective, back in '94, he's like, yeah, this is an experiment that failed. But it's okay because C has other good things going for it beside the syntax. Now, this raises an interesting question. What if C's success was not caused by its syntax, but rather its syntax became popular because C did? It's worth noting that just because something ends up being popular, that doesn't necessarily imply that every single aspect of that was good. It's possible that some aspects of it were good and those caused its popularity, and that other parts of it were bad, but they weren't so bad that they caused it to fail or caused it not to become popular in the first place. And putting these two factors together, Strauss Trip saying, look, I think this syntax was failed, but ultimately it had other things good going for it. That seems like a trade-off that a lot of people could make, and that could result in C becoming very popular over time, despite its syntax. Now, if that's a reasonable question to ask and a reasonable line of thinking, we can ask the same question of C++. What if C++'s success was not caused by object orientation, but rather that object orientation became popular because C++ became popular? What if that's true? Well, how might we go about investigating that? That's a difficult claim to substantiate. So Strauss Trip actually has a second section of his talk after he's done talking about C with classes, where he talks about like why C++. And it turns out the reason he created C++ had a lot to do with how C with classes turned out. So he says C with classes was a medium success. It allowed medium improvements only. That is to say, in comparison to C, it was just a relatively small improvement. It was a medium improvement. And so as a result of this, the community around C with classes was not very big. In other words, it just wasn't that popular. It's like, yeah, this has some nice stuff. In addition to the OO stuff, he also added stronger type checking, which, as he talks about in the interview, was really kind of his main motivation. And he just saw classes as a way to orient those types that he wanted to be stronger than C's type checker. But at the end of the day, it just wasn't big enough. And he felt that he was stuck with this dilemma where he was the sole maintainer. And as far as he could tell, he was always going to be the sole maintainer. He didn't want that. So here's Strauss Trip again talking about how he thought about how to get out of that dilemma.
There seemed to me to be exactly two ways out of the dilemma. I could either improve the language so that it could provide more benefits to the users, allow people to write code better, make greater changes to their organizations. That would make the language more popular, would get more users, and that would allow to pay for the infrastructure that it needed, supports development, teaching, compilers, porting, that kind of stuff. And the alternative was, of course, to stop supporting C with classes, and then the users would go away, and that would solve the problem. On the other hand, the users were my friends, and just dropping them that didn't seem to be fair at all. I later learned that actually was a third alternative, but I'm somewhat pleased that I didn't think of it at the time, because the third alternative, which is sort of a conventional solution, is simply to add hype, more advertising, more glosses, talk people into using it. But fortunately, I didn't think about that at all.
Okay. So he summarizes by saying, look, there were only three ways out of this dilemma of C with classes where it wasn't popular enough. One possibility was I could add features. So I could try to improve the language so that it would become more popular, and maybe I wouldn't be the sole maintainer anymore. I could drop it, but I didn't really want to drop it when my friends were using it. Or I could try hyping it, which fortunately I hadn't thought of at the time. But this has an interesting implication about it. I mean, essentially he's saying when the language was just C and it added only the OO features, its lack of popularity was a dilemma. And in fact, it wasn't just the OO features, it was actually OO features plus additional static type checking, like stronger type checking. And that still was not enough for its popularity. So until he had added the non-OO features and renamed the language to C++, it didn't take off. So going back to this question, what if C++ success was not caused by OO, but rather that OO became popular because C++ did? He did that experiment very directly with C with classes. He took C, he added OO, and the result was that it was not popular. Exactly the story of C with classes is that adding object orientation to C was not enough to cause the popularity that C++ got. In fact, it was explicitly the non-object oriented features that he added that became the catalyst for it becoming the massively popular language that it is today. And looking back at this in hindsight, it's actually maybe not that surprising because if we look at OO features sort of as a category of what are the features that are in this paradigm and how do they stack up against other non-OO features found today, the results are maybe somewhat surprising. So inheritance, encapsulation, methods, objects, these are all object-oriented features. These are things that you find in the object-oriented paradigm from a language feature perspective. There are other language features that a lot of these languages have today that are unrelated to objects. For example, composition, modules, first-class functions, and records. So comparing these two side by side, let's look at inheritance and composition. Well, since the mid-90s, the recommendation has been, you know what, rather than inheritance, you should prefer composition over inheritance. There's that phrase, prefer composition over inheritance. And this is widely discussed among object-oriented thought leaders. Inheritance is, in fact, explicitly disfavored in favor of composition. Encapsulation, like we talked about earlier, is sort of a weaker form of modules, and every single one of these languages ended up concluding that they wanted modules anyway, even though they already had encapsulation. So it's essentially just modules for objects, but you end up wanting modules anyway. Methods, in the absence of inheritance, are essentially just functions that are scoped for objects, and they're not first class, so you can't pass them around the way you can with first class functions. A lot of these languages ended up getting first class functions. Even Java now has lambdas, C++ has lambdas, Python has lambdas. And finally, when you come to objects themselves, if you've already concluded that we don't really need inheritance, encapsulation, or methods, they're not really all that great compared to composition, modules, and first class functions, what do objects have over records? Well, they're essentially just records where we've decided that we're going to use them for mutable state, and that's about all they are. So zooming out and looking at all of these in aggregate, it's sort of like every object-oriented feature now, 4 decades later, has become some combination of disfavored or redundant with other features that we've concluded are things that we want anyway, even if we have those OO features. And this has ended up being sort of like the bread and butter stuff that every language agrees that they want, even if they had the object-oriented alternatives before then. So looking at that lens, it's like, well, maybe it's not that surprising that C with classes ultimately was only a medium success, as Strauss Trip said, because it turned out there were like better versions of all these things that were sort of right around the corner. So Strauss Trip's perspective was, hey, these features weren't valuable enough, so solution to that was to add non-OO features and rename the language to C++. But what about Alan Kay's perspective in terms of object-oriented design? We talked about paradigms or features, but also style. And Alan Kay was the designer of Smalltalk, and he coined the term object-oriented. And he has a lot of strong things to say about object-oriented style and object-oriented design. We talked about structural programming earlier, so by means of contrast, I'm going to talk about structural style. This is in my own words, my own definition for what I would say structured programming style is. It's about organizing your program's control flow into blocks rather than go-tos or jumps. Similarly, in my own words, I'm going to define what I would say object-oriented style is, according to Alan Kay, but these are my words. Organize your program around stateful entities which isolate their state and communicate by message passing. Alan Kay mentions in other talks that he's like really big on the idea of objects must communicate via message passing. That's, as he sees it, a central idea of object-oriented programming. But let's not use my words. Let's look at what Alan Kay himself says, even though it's a little bit longer-winded. Smalltalk is a recursion on the notion of the computer itself. Instead of dividing computer stuff into things each less strong than the whole, like data structures, procedures, and functions, each Smalltalk object is a recursion on the entire possibilities of the computer. Thus, its semantics are a bit like having thousands and thousands of computers all hooked together by a very fast network. Smalltalk's contribution is a new design paradigm, which I call object-oriented. So sort of condensing this thing down, essentially what he's saying is object-oriented semantics are a bit like having thousands and thousands of computers all hooked together by a very fast network. That's the idea of the design, how you're supposed to organize your programs. Does this sound familiar to anyone? There's another thing that is described this way, and this time I'm going to quote Wikipedia. Distributed systems is a system whose components are located on different networked computers which communicate and coordinate their actions by passing messages to one another. Putting these things together, essentially Alan Kay's philosophy for object-oriented programming and object-oriented design and how to style your programs in an object-oriented way is organize your program like a distributed system. Now, maybe in 1967, when he said that, these connotations were maybe different than they are today. The idea of saying you should go out of your way to make your code as much like a distributed system as possible, maybe that sounded like a good idea. But to me, with the benefit of hindsight in 2020, this is a frightening idea. Distributed systems have developed a reputation over the past several decades as one of the hardest aspects of programming. And granted, some of that has become because of error handling, and that's not really something that comes up when you're talking about objects communicating. They don't really have network failures and stuff like that. But just from an architectural, organizational perspective, distributed systems are notoriously complex and really, really hard. And the general advice is, if you can avoid having a distributed system, you should. So the pitch of organize your program like a distributed system, I would say, has really not aged well. Knowing what we now know about distributed systems, this does not sound like a great way to organize your program. So it's worth noting, though, that like the original idea of objects was simulations. And in that context, this actually doesn't sound unreasonable. Organize your program like a distributed system of millions of independent agents in a simulation. Well, yeah, the whole point is that they're independent, and you want to be able to introduce new ones on a fly, kind of like you do in a network, and have them all interact with one another and just sort of bounce off one another and impact one another's state. Yeah, it kind of sounds like the original idea for objects in Simula was a pretty reasonable design. Remember, the difference between objects and object orientation is that object orientation is about taking this concept that was special purpose for simulations and saying, what if we applied that to everything? And it's that idea, the object orientation, the idea of applying this special purpose niche tool for simulations to everything, that in hindsight doesn't sound like a great pitch anymore. Okay, so talking through the Strauss Trip stuff, we ended up concluding that OO features are some combination of disfavored or redundant in the year 2020, and OO style of be more like distributed systems has really not aged well. I want to emphasize that this is not to say that the people who came up with these things did anything wrong. They were working with the information that they had at the time, which was decades ago. But the point of this talk is not to talk about just what happened in the past, but also what's going to happen in the future. And so it's relevant to ask the question, how did these experiments turn out and how well have they aged, knowing what we now do about all these other language features and all these other programming styles. So let's ask the question, is object orientation, is this what the future looks like? Are we going to keep doing this? Is it always going to be the most popular languages are all object orientation? Or is object orientation an experiment that we tried and we learned a lot from it along the way over the decades? But ultimately, this is a step on the road to the next paradigm shift. And is there going to be another paradigm shift away from this? For my money, I think the evidence is pretty clear that, yeah, we're going to move on. We're going to find something else. So one example of what the next thing might be is for C++ programmers. Now, granted, this is something that I think is pretty specific to C++ programmers, but it's an example of a community saying, you know what, maybe object orientation is not actually all it was cracked up to be. Let's orient around something else instead. This is a talk Mike Acton gave at CPPCon 2014 called DataOriented Design, which he's pitching as an alternative to object-oriented design. For context, he works at a game company. They make really high-performance game engines. And as you can see on this slide, they use about 70% of their code is C++, but their most preferred language to work in is assembly. And the reason for that is that it's the most low level, and they really, really, really care about performance. So I'm going to summarize his pitch for data-oriented design. This is my words, not his, but as data-oriented design is about design software around hardware so that it runs faster. So it turns out that object orientation, among other things that it does, is it isn't great for how memory wants to be organized. Like if you orient your code around objects and these sort of like distributed things, you get things like memory fragmentation. There's various problems in terms of performance that are sort of downsides if you're trying to make really high-end, high-performance AAA game engines. So what his pitch is like, essentially the subtext is object orientation doesn't seem to be necessary or maybe even that helpful for organizing code to be more maintainable and easier to understand. So let's just scrap it, and instead let's focus on what does the hardware want us to do? Because that's how we're gonna get the maximum performance, and we can find other ways to structure our code so that it's still maintainable with that constraint. Now, I'm not a member of the C++ community. Last time I used it was in college, but it is at least somewhat telling that 4 years later, at CPPCon 2018, there was another talk called OOP is Dead, Long Live Data-Oriented Design. Now, I would not go that far. I think it's an exaggeration to say OOP is dead. Clearly, it's still, all of the top languages still use it, but it is reasonable to ask the question, has OOP peaked? Is it something that is no longer going to be the future? And I think the answer to that is yes. There's an important distinction here, though, between what C++ programmers are doing and what all the other languages on that top list, that top 10 list were doing, which is garbage collection. Whether you're going to garbage collect or not to garbage collect is really kind of a bright line as far as performance goes. If you can afford to have a garbage collector, generally speaking, your performance requirements are lower, and something like data-oriented design isn't necessarily going to be as appealing because you're not trying to squeeze every last ounce of performance out. You're not saying, we use C++, but our most preferred language is assembly. Most companies, most organizations, most even individuals are not in that place. So let's look at the other side of this, the garbage collected languages, the languages that most of us are using day to day. What's the next potential paradigm that those languages are going to go towards? So that brings us to the final part of the talk, the next paradigm shift. So we talked earlier about the concept of paradigms being both features as well as styles. And if the language doesn't have the features that are associated with that paradigm, it's still often possible to emulate those features by using the features the language does have. So structured COBOL was an example of this. COBOL did not have blocks. It did not have if, then, else. But you could still write structured style COBOL, and it was a popular thing to do that. We also talked about modular programming in C as an example of this. Even if you don't have modules as a first-class concept in your language, you can still organize your code in sort of a modular way and pretend that you have the feature of modules and just do what you can with the language features you have. These concepts of structured COBOL and modular programming in C might sound familiar to anyone who's been in the programming community the last 5, maybe even closer to 10 years, because these days we don't see structured X or modular X, we see functional X. Functional JavaScript, Python, Java, C++, C#. You really can't throw a rock without hitting some language where there's multiple books, multiple blog posts, articles written about how to write that language in a functional style. So why might this be? I mean, a paradigm is about not just features, but also about style. Why is it that so many people are trying the functional style in these languages that are not first-class functional programming languages? Well, if object-oriented style is organizing your program around like a distributed system, I would say, again, my words, that the functional style is about avoiding mutation and side effects. So why is that a good idea? Like, why is functional programming something that so many people would be interested in? Well, simply put, it's because functional programming is a solution to complexity. And there's essential complexity, and you got your incidental complexity, and okay, just kidding. But kind of not. I mean, in the sense that functional programming, like object-oriented programming, is tackling the same problem because object-oriented programming didn't solve this problem. It's sort of trying something else. Like Dan Ingalls said, object-oriented programming was an experiment. It was something they were trying to solve some of the complexity they encountered. And in the same way, people are now giving functional programming a real shot as a solution to that problem. So why might functional programming in particular seem like a good solution to complexity? Well, functional programming seems like a promising way to reduce complexity, I would say, because it makes our programs less like distributed systems at every opportunity. In that sense, functional style is essentially the opposite of object-oriented style. And I know that people disagree with me about this. I've seen talks saying, actually, functional programming and object-oriented programming have a lot in common. But fundamentally, when it comes to the style, I think they are diametrically opposed. They're about approaching the same problem from basically the exact opposite direction. So if you think that object-oriented programming has not been successful at addressing complexity, there's good reason to believe that functional programming might, because it's essentially saying, let's try the opposite approach. So Alan Kay's quote about instead of dividing computer stuff into things like data structures, procedures, and functions, we're going to try and have thousands and thousands of computers all hooked together by a very fast network, metaphorically. Functional programming is essentially the opposite. Let's say, no, let's use data structures and functions, and that's it. Instead of trying to organize our code as if it were thousands and thousands of computers hooked together by a very fast network like a distributed system. So you might be wondering, like, what are people saying about this stuff? You may or may not have heard various quotes about functional programming, but I think this particular quote is one that is more important than a lot of the other quotes about functional programming I've seen. No matter what language you work in, programming in a functional style provides benefits. You should do it whenever it is convenient, and you should think hard about that decision when it is not convenient. Now, the reason I think this quote is important, because if you look at it, you might say, well, obviously this is some ivory tower academic person who's advocating for the functional style, or maybe they're trying to sell something. This is John Carmack, who is a high-performance C++ programming legend who created Doom and Quake and was the CTO of Oculus. This is about as far from the ivory tower as you can possibly get. And this is someone saying, no, actually, I have tried this style, and what I've found is that it provides a lot of benefits to the point where this should be the default way that you write code. And if you're not going to write code in this style, you should think very hard about that decision. That, to me, is a very important endorsement of this as an alternative to object-oriented programming. Other endorsements that we've sort of seen implicitly come from modern languages, at least in terms of interest level. So Kotlin, in their FAQ, Kotlin, by the way, if you're not familiar with it, is a language that's sort of the successor to Java in some ways. It's sort of like Java++. It takes Java and then builds on it, but has complete backwards compatibility with Java, much like C++ did with C. In Kotlin's FAQ, one of the questions is Kotlin an object-oriented language or a functional one? You would never see this question back in the swearing in church era of the 90s. There's no chance you would see an FAQ, like a frequently asked question about whether the successor to Java would be object-oriented or functional. Of course it's object-oriented. Who uses functional? But these days, there's way, way, way more interest in that. And the answer is, don't worry, Kotlin has both object-oriented and functional constructs. You can use it in both OO and FP styles or mix elements of the two. So this is Kotlin saying, hey, we understand that there's a shift happening here, and we're a part of it. Don't worry. You can use either object-oriented style or functional style. We have good support for both. Swift is another example of this. So Swift is the successor to Objective-C, another dedicated object-oriented language. And on their page, they don't even have in the FAQ, they just talk about some of the other features of Swift include functional programming patterns like map and filter. They just go out and volunteer that you can have support for programming in a functional style in Swift, because these days that's viewed as an asset. So where does functional programming fit into sort of our timeline of programming paradigms? Believe it or not, it's actually a lot earlier than you might think. Lisp is arguably the first functional programming language, which came out in 1958. So that was sort of the first language to offer functional programming. And I actually say that it happened slightly before structured programming even, like before if-then-else blocks, Lisp was a thing. I looked this up. The committee that made Algol, that designed Algol, the language that introduced if-then-else for the first time, one of the people on that committee was John McCarthy, who created Lisp. And apparently at the committee meeting, he actually suggested introducing structured programming to Algol based on his experiences having done if-then-else in Lisp. So actually functional is after procedural, but before structured and object-oriented and modular, at least in terms of history. Lisp had things like conditional expressions, so i.e. structured programming, garbage collection. This is the first garbage collected language. We've had that since 1958, and lots more. Worth noting that garbage collection is an idea that was around a long, long time ago, but did not actually gain traction for decades afterwards. It was just sort of sitting on the shelf. And the things that people said about garbage collection at the time are, this is academic ivory tower impractical stuff. And the reason at the time was it was too slow. People would say you cannot have a garbage collector and automatic memory management like that. You just can't afford it. Now these days, of course, everyone's changed their tune. They say, of course, garbage collection is a very normal way to do things. Of course, garbage collection is great. Garbage collection has become the norm. So it's worth noting that just because something is initially dismissed as academic ivory tower stuff and sits on the shelf for decades, that does not mean that there will not become eventually a shift to using that thing ubiquitously. And there's a reasonable case to make that functional programming is kind of the same way. This thing that sat on the ivory tower academic shelf for many decades, and only in the past like 5-10 years has it started to see an uptick in the industry. So after Lisp, you have C in 1970, which we already talked about. ML is sort of the next big functional influential language. This introduced type inference. So it was the first language to have type inference. ML had 100% type inference. If you've used a language with type inference these days, usually there's some sort of asterisk like, well, we have type inference, but in these certain cases it doesn't work, and sometimes it gets it wrong. ML, 100% never got it wrong. And the descendants of ML today, such as Elm, OCaml, they still have this, 100% type inference, never gets it wrong, never need a type annotation. ML also introduced generics, which Java got in version 5. Standard ML, which was the successor to ML, introduced modules. You notice in that timeline that standard ML came out after modular programming became a thing in Modula, but ML came out before it. C++, remember, came out after standard ML, which had adopted modules, but C++, Strauss Trip did not choose to add modules to his language, possibly because he wasn't aware of them. But again, these being academic languages, they were very aware of the latest stuff going on in programming languages, and they, at least at that early era, had already decided modules are a good thing, we should put them in standard ML. Haskell, another successor, introduced, well, didn't introduce, but popularized laziness. Miranda introduced laziness, but, and Haskell is one of the ML descendants that's become most widely used in industry today, while still in the grand scheme of things remaining very, very niche in the scope of all programming languages. Worth noting that all of these languages were research languages. It's not just that they sort of sat on the shelf in academia because they necessarily weren't good, but rather because that's just the only people that were exposed to them. People in industry, there was really no uptick, there was no push, there was no interest. Everybody was doing object-oriented stuff. Object orientation did not come out of academia. It was created, as Dan Ingalls talked about, because they were building an operating system and a graphical user interface. That was their job, to build commercializable software. And so it's kind of no surprise that with object orientation coming from Smalltalk and from C++, which also, again, he was working in New Jersey for commercial projects, that those ended up getting industry adoption way before people were taking a serious look at functional programming in industry. But now that's changing. So again, we talked about a paradigm is about features and style, talked about the functional style. So let's talk about features a little bit. We mentioned briefly that features in object-oriented languages have all turned out to be some combination of disfavored or redundant. And the good ones that people end up using actually have turned out to be sort of unrelated to objects. The features that you find in FP languages tend to include those same things that we talked about as being good. Composition, modules, first-class functions, records. Standard ML had all of those in 1975. And now, modern languages have all sort of ended up with these things as well. There's one that I would add to modern FP languages that has become sort of like a popular thing, which is first-class concepts of immutability, like baked into the language. Worth noting that the fact that FP languages do not have all of the object-oriented ones has a pretty profound effect on their ecosystems. When people are building libraries and sharing code around one another, all of the primitives that they're building on are these, which makes for a lot simpler and a lot more consistent of an ecosystem than when you have sort of a hybrid world that has all the OO stuff that we've sort of moved away from and all the new stuff that has sort of emerged as like a better alternative to it. So to this question, we asked, why don't we have both about structured programming? Why don't we have both Goto and if then else? You can ask the same question, why don't we have both object-oriented programming and functional programming? Why don't we have languages that have both? Isn't more better? Well, there are languages that are explicitly hybrid OOFP languages, and they sort of self-identify that way. Examples would be Scala, OCaml, and F#. So I've talked to people in these communities. I'm not a big user of any of these languages, but I've asked some people, what they thought about how people use those languages in terms of the OO features and the FP features. One sort of a Twitter result that came out of this is Runar Bjarnason, who's like a big member of the Scala community, just took an informal Twitter poll about, hey, if you use Scala, how do you use it? Most people responded, I just use it as an FP language primarily. And less than half, but close to half said, I actually use it as a hybrid FP and OO language. Worth noting, Runar is the author or the co-author of Functional Programming in Scala, so his audience is probably skewed based on that. But when I talk to OCaml people, the response is pretty overwhelming. Everybody in the OCaml community overwhelmingly uses all the FP features and pretty much disregards the OO features, and F# was somewhere in between. So it doesn't seem to me all that convincing that the OOFP model is necessarily a big advocate for the concept that this is better. If you talk to people who use these communities, it seems like pretty consistently the way that people are using them is mostly as functional programming languages, and then they're using the object-oriented features sort of when they have to, or maybe in some cases as like an actual mix of both. But I don't think the case is there that this is better. It seems to me, if anything is the case, a lot of people are using these languages as a gateway to functional programming. And I've definitely heard that sentiment expressed a lot in the Scala community in particular. Okay. Worth noting, though, that the concept of hybrids sort of goes against the pitch for functional programming as a means of reducing complexity, because the way that it reduces complexity is not through adding more features, but through subtracting things. We talked about the functional style is about avoiding mutation and side effects. It's about subtraction and saying, let's take away these foot guns, and then our code will be less complex and easier to understand. There's a step further that you can go, which is the pure functional style, which is don't even support mutation or side effects. And that's where you actually start to get some features, some new things that are no longer, that aren't really possible if you're just following the style, but which sort of require actually taking things out of the language in order to unlock other things. So as an example of what the pure functional style looks like, let's say I was writing some JavaScript code in a synchronous style. So I'm reading some author info out of a database, I'm reading some posts out of a database, say author equals database.read, posts equals database.read. So after this, I've gotten the author, and then I want to get the posts for that author using some information that's stored on the author. So a downside of doing things synchronously is that they block. If you're running this on like a web server, say, you don't necessarily want to have all of your operations be blocking because that ties up the CPU waiting on these operations when potentially it could be servicing other requests. So there's become sort of an increasingly desirable best practice to do asynchronous style programming because it's better for performance. So the first way that you saw this in like Node.js was an async style via callbacks. So you'd have same database.read calls, but instead of saying author equals, you would pass a callback function. This is because JavaScript has first-class functions that would accept the author, and then inside the body of that function, it would do another database.read using the author's ID or whatever the case may be, and then it would have another nested callback inside that for how to handle the resulting posts. But a lot of people found that this didn't compose very well and felt kind of clunky to use, and so what's ended up being the best practice is promises, where you have sort of an abstraction around this chainable asynchronous effects concept, and you chain them together using .then. So this has become, this bottom one has become sort of the best practice in JavaScript. And actually you've seen syntax sugar around this like async await to try and make this even nicer because it's become such a like best practice way to do things. So even though synchronous and async via callback are available, in practice what people are encouraged to do is to use promises this way. So the difference between JavaScript, which is an imperative language that does allow side effects, and a language like, for example, Elm, which is compiled to JavaScript, is that in Elm, you have this code instead. You'd say db.read, and then that's the pipe operator, which is basically a way of chaining these things together, much like you would a promise. Say, and then get the author, do another db.read, and then take the post that results from that, and then do whatever you're going to do. So this has the same sort of fundamental design characteristics as promises. And if you looked at code using this, which is using what's called task in Elm rather than promise, side by side, you'd be like, yeah, this looks structurally very, very similar to me. The only difference really is that when you instantiate a promise, JavaScript runs the side effect immediately. Whereas in Elm, when you instantiate a task, it's just sort of a description of the operations that you want. And only when you sort of hand that off to like your main, does it actually get executed by the Elm runtime. So that difference alone is essentially the difference between pure functional programming and everything else. This is the only way to do it in Elm. You don't have the synchronous or the async with callbacks option. The only way that you have to do programming is this asynchronous way. But again, that's sort of the best practice. So it's not really that big of a downside. Being forced to do things in the best practice way is arguably kind of good. So when you compare these side by side, they're pretty similar, and people coming from JavaScript to Elm, in a lot of cases, this is not really where the learning curve comes from. So the term for this is sort of managed effects instead of side effects. You build up this description of the effects that you want, and then the runtime is in charge of actually executing them. Other languages where you can find managed effects include Haskell, Idris, PureScript. They all sort of follow the same basic idea. They're all pure functional languages. So managed effects is something that goes beyond just the style of functional programming. This is something that actually has benefits that you cannot get at a language level unless you're willing to go as far as to say, this is going to be a pure functional language where we're not going to have mutation, we're not going to have side effects. Those are just things that we have subtracted from the language. So an example of a thing that managed effects can get you is, let's say I declared 3 things in a row, x equals blah, y equals whatever else, z equals something else. And later on, they got pretty big. Like I have maybe, quite a substantial amount of code behind each of these. In a pure language with managed effects, I can reorder these. I can shuffle them around, and the order of declarations just does not matter anymore. Because none of these can potentially do side effects, none of these can mutate anything, the order just doesn't matter. I literally can shuffle up my declarations in any order, and it's always going to produce exactly the same program at the end of the day once it's been compiled. So this means that reorganizing code in the small is much less error code, and also in the large, it ends up being much, much less error prone. We talked earlier about sort of the spaghetti code of Gotos everywhere and how that really messes up control flow. When I looked at this diagram, I remember thinking, wow, this actually reminds me about the benefit of pure functional programming, which is these arrows are not about control flow, but rather I can move stuff around anywhere. I can take this thing and say, you know what, this actually ought to go over here. Or as my program gets bigger, I say, you know what, I want to pull this chunk out and move it into a shared module. I can do that really, really easily because the order doesn't matter. And every single function that I'm calling has no side effects, so it doesn't matter if it was called before or after other functions. All that matters is, am I able to give it the arguments that it needs? And am I doing the right thing with the return value that comes out the other side? The people I talk to who have used pure languages, like I have for the last 5 years, and talk about refactoring say pretty consistently that if you don't have managed effects and you don't have a complete lack of mutation and side effects, you cannot get this experience, which is second to none in terms of how easy it is to refactor and reorganize your programs. This is a concrete benefit that comes from a language level benefit of functional programming, not just the style. You cannot get it from a hybrid or from writing JavaScript, Python, Java in a functional style. Okay, so going back to this earlier thing, structured programming, hey, if we can express everything with blocks, why keep the Goto foot gun? Pure functional programming, the pitch is essentially exactly the same thing, but applied to side effects. Hey, if we can express everything with managed effects, why keep the side effects foot gun? I mean, promises are already best practice. Tasks are almost the same thing in terms of how your code's structured. Why bother keeping around the side effects? One way of expressing this might be side effects considered harmful. And it's a reasonable question to ask. If there are people who are having a good experience with this and the downside is so minimal, why not get the upsides? Why not indeed? Okay, so to sum up, we talked about a bunch of different paradigms here, a bunch of different concepts. Initially, we talked about COBOL. It was first developed in 1959. Eisenhower was president. Alaska and Hawaii were just becoming states. And although for a very long time, it was the #1 most popular programming language in the world, over the decades, it eventually peaked and then declined to the point where today we now look back on it as a historical relic. And I want to reemphasize this story because just because something is #1 today and something that we all take for granted as the way the world is, does not mean that it will not eventually peak and then decline and be replaced by something else. I think today, object-oriented programming is in the same position that COBOL was then. It's about to peak or is currently peaking, and it's about to start declining over the next several years. We talked about the structured programming paradigm and how we had a sort of paradigm shift away from this conditional-based jumping that results in spaghetti code to blocks of code for conditionals, loops, procedures, etc. We talked about how, although object-oriented programming became very popular, so popular that languages that didn't have it started adopting the style, and it got to the point where criticizing OOP was rather like swearing in church, which I guess means I've done a lot of swearing in church in this talk, apologies. It ultimately was something that, that did successfully take over the world. There was C and OOP, this is in 2019, among all the most popular languages. Clearly, this is a paradigm that has taken over everything. Looking back at the original pitch for object-oriented programming back in 1989, the claim was, look, this is a solution to complexity. Like we did these experiments, we found something that really works to solve complexity. But now in 2020, looking back, it seems clear that it really didn't live up to that expectation. The goals of the experiment ultimately were not met. And in fact, it's not really clear to what extent object-oriented programming really helped with reducing complexity. Alan Kay talked about, I made up the term object-oriented. I did not have C++ in mind. Strauss Trip was coming from a different perspective, and Simula was sort of the common ancestor between their two approaches. Strauss Trip focused more on the language benefits. Kay focused more on the design benefits. But Strauss Trip ultimately found that the language benefits were not there. When he made C with classes, i.e. adding object orientation to C, what he ended up with was a dilemma of popularity. And it was only until he added non-object-oriented features and renamed to C++ that the language became popular. And the features that were found in OO languages, with the benefit of hindsight, all ended up being replaced as sort of disfavored or redundant with other things that all these languages, including the object-oriented ones, ended up wanting anyway. Object-oriented features ended up disfavored or redundant. Object-oriented style of essentially be more like distributed systems really doesn't sound that good now that we have learned a lot about distributed systems and how they've worked out in terms of complexity. In fact, it actually sounds like that's a recipe for more complexity, not less. So we asked the question, is this what the future looks like, or was object orientation an experiment that we tried and learned a lot from and has now peaked because we're ready to move on? I think the answer is yes. Evidence of this is that a lot of people are now trying out the functional style. There's books, articles, blog posts, talks all over the place about how to apply this style to programming languages that are already popular today. I think the reason that functional programming seems like a promising way to reduce complexity is that it's about making our programs less like distributed systems at every opportunity. Essentially, going the opposite direction from what Alan Kay advocated, which is to say, try to conceptualize our programs as thousands of computers talking together over message passing instead of data structures, procedures, and functions, and instead say, no, let's embrace data structures and functions and do that instead of object orientation. A paradigm, as we've discussed, is about features and style. That's the object-oriented style. The functional style is about avoiding mutation and side effects as a means of reducing complexity. And the way that it does this is essentially through subtraction. Functional style is about avoiding that, and then there's a step further, which is the pure functional style, which is to say we're not even going to support mutation or side effects, at which point you can get language-level benefits. We talked about hybrid OOFP languages, which in practice tend to be mostly used as FP languages, with a minority of people using them as actually, we think hybrid is the best, FP and OO together, even languages where that's explicitly the goal of the language. And finally, we talked about managed effects instead of side effects and how there's a lot of similarities structurally between managed effects and sort of the current best practice of promises or futures or whatever you want to call them, but the fact that managed effects get you additional benefits at the language level. We talked about the history of all these languages and how these are sort of all research languages that for a long time, much like garbage collection, just sort of sat on the shelf and only very recently have become sort of adopted in industry and become widely used, like object orientation, which originated in industry and has been growing ever since. And finally, I want to point out something about this timeline, which is that look at how long these things took. The very first data point on this, all the way back in procedural programming that we started talking about, was the 1950s. That was more than half a century ago. And we've come so far and learned so much about programming that, yeah, I mean, the fact that I'm saying that a paradigm shift is happening really should not be that controversial because these paradigm shifts take decades. They occur over a very long period of time. Modula came out well with enough time for C++ to have modules, but it just didn't have them because it wasn't on board with that. It wasn't clear yet that that was a good idea. So if you feel like, hey, I'm not sure about this functional programming thing, is it just going to be a fad? Is it really the future? I would encourage you to take a look at the history and look at really asking the question, like, what has object orientation gotten us and what could going in a different direction get us in the future? If you're curious about more of the history of how we got to where things are today and why these languages became popular, I gave a talk last year about this called Why Isn't Functional Programming the Norm? Why are these other top 10 languages the norm? Plenty more history in there if you're interested in this stuff. Thanks very much.